Okay, in this example, we are going to take a look at a random variable x, and let's assume it's continuous, and it comes from a distribution with PDF given over here. So we have two parameters, lambda and delta, and here's a formula for the PDF, and we're assuming here that values of random variable x are strictly greater than delta. Both of these parameters are positive. And so we want to find the first and second theoretical moments of x. And so to find the first theoretical moment, that's mu, or now we could denote it with mu sub 1, we're going to find the expected value of x to the first power. So that means if we're dealing with a continuous random variable, we're going to integrate from delta up to infinity x times f of x. And so the delta comes from the fact that our domain is x is bigger than delta. So we're going to integrate from delta up to infinity x times lambda e to the minus lambda x minus delta. So that was our given PDF function. So we would need to evaluate this, and here the variable is x, and we're treating the parameters as constants. So here we can use integration by parts. Using u is equal to x, and then we could define v prime as the rest of this stuff, the lambda e to the minus lambda x minus delta. And so this is a good candidate for integration by parts because when I take the derivative of u, I get 1, and when I integrate v prime to find v, I can do that and I get minus e to the minus lambda x minus delta. And now the resulting integral of u prime v, I would be able to integrate. So skipping some of the details, using integration by parts, we would get that the first moment is delta plus 1 over lambda. And then I'm looking for the second theoretical moment, we'll call this mu sub 2. Well, that would be the expected value of x squared. So again, we would integrate from delta up to infinity. And now we're going to integrate x squared times f of x. And our f of x is still the same. It's the lambda e to the minus lambda x minus delta. And for that one, you would need to use integration by parts 2 times. So it's not trivial to integrate that. It's maybe a little tedious, so I'll skip that detail. But you can verify, in that case, you would get delta plus 1 over lambda, all of that squared, plus 1 over lambda squared. So those would be our first and second theoretical moments of x. And if I wanted to calculate the corresponding first and second sample moments, which is being asked in part B, where now we have a sample where the first value is 3, the second value 4, and 5, and then 8, well, these go much easier, right? So our first sample moment M1 is just the sample mean x bar. So for that, we would take the 3 plus the 4 plus the 5 plus the 8, divided all by n, which in this case is 4, and that gives us first sample moment equal to 5. And for the second sample moment, this one we would square each of the values. So this would be 3 squared plus 4 squared plus 5 squared plus 8 squared, all divided by 4 again, and in that case the second sample moment comes out to 28.5. Okay, so one thing to make a note of here is that when we calculate our two theoretical moments in part A, these are dependent upon these parameters delta and lambda, but there's no dependence on x here after we integrate with respect to x. And when we calculate the first and second sample moments, we can actually calculate those values. So those are going to be constant values. In this case, we got 5 and 28.5. So the theoretical moments are going to depend on our parameters. The sample moments are going to be values that we calculate from our sample. And the method of moments is going to be an estimation method where we're going to line up each of our theoretical moments with each of our sample moments. So we'll outline that process on the next slide.